What if I told you there's a technique that can take a clunky, slow algorithm and make it, well, blazing fast? A single pattern that unlocks a whole bunch of tricky coding challenges involving arrays and strings? Okay, let's get right into it. We're talking about the sliding window.
To get our heads around this, imagine you're on a train, looking out the window, and you want to find the most beautiful 3-second stretch of scenery that goes by. So what do? Do you, stop the train, get out, and walk all the way back to the beginning to recheck every single view from scratch? No way, of course not. You just keep looking, right? As one tree leaves your window frame, a new one comes into view. You're constantly updating your idea of the best view so far based on this smooth flowing change. And you know what? That simple, intuitive idea is the absolute heart of the sliding window algorithm. So let's take that train analogy and really build a solid foundation on it. In this first part, we're going to nail down exactly what we mean when we say a window on our data. Okay, here's the more formal computer science-y definition. It's basically an approach where you look at a specific continuous chunk of an array or a string. That's our window. And here's the key part. Instead of recalculating everything from zero each time you move, you just incrementally update the information. It's all about being efficient. Let's try another visual. Picture a really long bookshelf, just packed with books. Now you take a little rectangular frame and place it over, say, 3 of them. When you slide that frame one book to the right, think about what actually changes. You only need to care about 2 things: the book that just left the frame on the left and the new book that just entered on the right. Everything else in the middle, it just stayed put. Now, this window of ours can act in 2 main ways. On one hand, you've got the fixed size window. The name says it all. It always covers the exact same number of elements. It just slides along nice and predictable. On the other hand, we have the variable size window. This one's more dynamic. It can actually grow or shrink itself to follow a certain rule, like find the longest stretch of books with no duplicate authors. So let's dive into that first type, the fixed size window. It's the perfect place to start because the logic is just so clean and straightforward. Here is a classic problem you'll see. We've got an array of numbers, and we need to find the biggest possible sum we can get from any continuous block of, in this case, 3 numbers.
Let's actually watch this thing in motion. So in step 1, we start with our first window, 2, 1, 5. Add them up, the sum is 8. So for now, our max sum is 8. Now, here's the clever part. To get to step 2, we are not going to re-add everything. We just take our old sum, 8, subtract the 2 that's leaving the window, and add the 7 that's just coming in. Boom, that gives us 13. We update our max sum. Let's do it one more time for step 3. Take our current sum, 13, subtract the 1 that's leaving, add the 3 that's entering, and we land on 15, our final answer.
And that right there, that's the secret sauce. Each slide is just one little subtraction and one little addition. That's what we call a constant time, or O of 1 operation. It means we can zip through the whole array by just touching each element a couple of times. It's incredibly fast. Okay, so we've got the fixed window down. Now let's check out its more flexible cousin, the variable size window. This is where things get really, really clever. So unlike our fixed window, this one changes its size on the fly. It has a mission, a kind of validity condition it has to obey at all times. For example, that condition might be, this window must not contain any repeating characters. The window will literally stretch and squeeze itself to make sure it's always following that rule. The whole thing is driven by 2 pointers, a left one and a right one, that mark our window's boundaries. It's kind of like a dance. First, you expand the window by pushing that right pointer out, adding new elements. You keep doing this as long as your condition is met. But the second you add an element that breaks the rule, you stop expanding. Now you have to start shrinking from the left, moving the left pointer in until the window is valid again. It's this constant rhythm of expand, check, shrink. And this powerful pattern can solve a whole class of really famous interview problems. Things like finding the longest substring with all unique characters, or the smallest subarray that adds up to at least some target number. These are perfect for the variable size window. So we know it's powerful, but how powerful exactly? And just as important, what are the traps we need to avoid when we're actually trying to write the code? This section covers that huge performance win and the common mistakes to watch out for. So here's the crucial point. With the variable window,
Both the left pointer and the right pointer only ever move forward through the array. They never ever go backward. What that means is, in the absolute worst case scenario, each pointer travels the entire length of the array, n, just once. So that gives us a maximum of 2n total movements.
And that 2n leads to this beautiful result right here. A brute force solution where you just check every single possible subarray would be O of n squared, which gets painfully slow on big inputs. The sliding window, with its linear 2n operations, is simply O of n. And let me tell you, that jump from n squared to n is a massive, massive gain in efficiency. It's why this technique is so important.
So here's a little cheat sheet for you. For both window types, that time complexity is a fantastic O of n. Now, the space complexity depends a bit on what you're tracking inside the window. If it's just a running sum, it's O of 1, constant space. If you're tracking something like character counts, it might be O of k, where k is the size of your alphabet or character set.
But it's not always a walk in the park. You gotta be careful. There are a few classic traps people fall into. First, that sum-based logic we talked about, it only works for non-negative numbers. A negative number can totally break the logic of when to shrink the window. A super common bug is using an if statement to shrink the window when you really need a while loop in case you have to shrink it multiple times to make it valid again. And of course, the old classics, simple off-by-one errors with your pointers can lead to a world of pain.
All right, let's bring this all home. Why did we just learn all this? Where are you actually going to see this stuff or even use it?
This is not just some abstract algorithm for a test. It's used in real-world systems all the time. Think about calculating stats over the last 5 minutes of data in a live dashboard. That's a sliding window. It's used in network monitoring to analyze traffic packets as they come in. APIs use it for rate limiting to check how many requests you've made in the last minute. And yeah, it is an absolute superstar in coding interviews.
So pro tip for you, if you're in an interview and you think this pattern fits, here's what you do. Before you even write a single line of code, state the rule of your window out loud. Say something like, okay, so for my window to be valid, the count of distinct characters must be less than or equal to k. That clarity shows the interviewer that you really truly get the pattern.
You know, the sliding window teaches us a really powerful lesson. Sometimes, to solve a massive, overwhelming problem, you don't need to look at everything all at once. You just need to look at the right things, one small, efficient step at a time. So the next time you face a huge problem, just ask yourself, could the answer be found by just looking through a smaller sliding window?